Hi, welcome to Module 4. So Module 4 is on sections 2.1 and 2.2, and both of those sections cover sets. This is going to be quite a shift from what you've been doing so far in the course. So you've been doing a lot of calculations, like especially with your calculator, and there are going to be very few calculations in this section, and all the calculations you do will not actually involve using your calculator or numbers, really. So yeah, it's a big change. And if you struggled with the last couple modules, this might be a nice break from that kind of stuff. So let's just jump in. So with section 2.1, we're going to just start by talking about what a set actually is. The definition from your book is that a set is a well-defined collection of objects. Objects is just a very vague word that can encompass a lot of different things. Basically, a set is just a group of something. And in life, we talk about groups of things all the time. We put names to those groups of things. So take, for example, like if you were a scientist and you were studying animals, there's all types of different groups of animals. So there's amphibians, there's mammals, there's fish, there's reptiles, and then within all of those groups, there's characteristics that we can talk about, like, can the animal swim? Does the animal have legs? Does the animal breathe air? Does the animal have a backbone? All of those different types of adjectives can put them in another group. And so with sets, what we can do is we can compare these groups. We can contrast these groups. We can see, like, okay, if one group isn't part of another group, we can put language to that. So anyway, so let's just jump in. We have, so right here, if an object is in a set, we call it an element or member of the set. For example, let's say that M stands for the set of all mammals. Okay, similar to what I was just talking about. We could say that bears are an element of M. Okay, and there's actually notation that allows us to say that even quicker, and we'll talk about it later on, but you can also say bears and use the symbol an element of M. So this symbol right here is an element of the set. Now, why did I pick M? I just picked that letter because mammals start with M. You can pick whatever letter you want. Usually we use capital letters to denote a set. So this example says, write the set of months of the year that begin with the letter M. So I could choose to use M again if I wanted to, just because months start with M, but you could use Z or any letter you want. So months of the year that begin with the letter M. So what's in that set? So notice up here, I described the set with words. So I just wrote out set of all mammals. Here, I'm not actually going to write, describe it. What I'm going to do is I'm going to use brackets. Okay, and I'm going to list out the elements in that set. So the months of the year that begin with the letter M are March and May. And then, so this set has two elements, March and May, and I can put them in any order. And then I use a comma to separate the different elements within that set. So as I mentioned, sets are always named with a capital letter. These are some standard sets or standard letters that we use for certain sets. So for example, capital N stands for the set of natural numbers. So if you're ever doing a homework problem and you see the capital letter N, you can just assume that they're talking about the natural numbers if they don't say otherwise. So for example, the natural numbers are all numbers that start, they're whole numbers, except it does not include 0. So the first natural number is 1, and then 2, 3, 4, 5. So think like counting numbers. Those are all natural numbers. No fractions, no decimals in there. I is the set of integers, and those are positive and negative whole numbers. So such as -3, -2, -1, 0, 1, 2, and while I'm at it, since I mentioned whole numbers, I'm just going to add whole numbers to the list too, just so you can see what those look like. So whole numbers are numbers that start like 0, 1, 2, 3, 4, So they're positive. Well, most of them are positive 0. We don't consider positive, but the set starts at 0 and goes up from there. No fractions, no decimals. It's very similar to natural numbers, except that it includes 0. And I always remember to remember the difference between whole numbers and natural numbers. I think about the O in whole, and I think, okay, that's kind of like a 0, so whole numbers include 0, natural numbers do not. So just a little way that I help remember that. So integers are positive and negative whole numbers, as opposed to just, the positive version down here, including 0. So, and then last but not least, E is the set of even natural numbers. And those would be like, if you look at our set of natural numbers, just those even ones. So the first one in the set would be like 2, 4, 6, 8, etc. Okay, so there's 3 ways that we can actually write out some sets, and you've already seen me write out sets so far. So you've seen me at the very beginning when I talked about the set of mammals, I just wrote out set of all mammals, and then with the months I listed it out using set notation with those brackets, and the same thing with these N, I, and E. These sets I use curly brackets. So anytime that you list out elements between, it says braces here, that's the same thing as curly brackets. And curly brackets, they are a part of your standard keyboard on the computer. So next to the letter P, you'll see a curly bracket, a left curly bracket, and the one next to that is to the right. So anytime you list out elements with curly brackets with commas in between, we consider that the roster method. So we'll just give an example here. So an example of roster method would just be a set like 2, 4, 6, 8. And it could have a ... or you could have a set maybe with something else where we call this a finite set, where it just ends. So it doesn't have to have the ... which is called an ellipsis. It could either end or go on forever. But the key here is that you have brackets, curly brackets, and that the elements are separated with a comma. So a description would be like what I did earlier. And if I said M is the set of all mammals. So that's the type that takes the longest to write, because you actually have to write it all out. And then the last one, I think this is the one that's probably the most confusing for students. It just takes a little while to get used to. It's called set builder notation. And if you've taken an algebra class, particularly like at Washtenaw, if you took like Math 097 or Math 169, this would probably be familiar to you. But if it's been a while, or if you didn't cover this in the last algebra class you took, it might be new. But basically what you're going to do, this part right here describes how you're going to use set builder notation. So you start by using curly brackets, and then you always put this horizontal line, or vertical line, sorry, in the next to the X there. And so you say all values of X such that vertical line means such that, and then you give a condition. So the way to describe the elements in the set. So for example, you could say N equals all values of X such that X is an even natural number. And actually, since we could even call this E, since we're describing the set of even natural numbers, which usually is denoted with an E there. You could also use shorthand notation like you see down here with this symbol here. That means is an element of. We could also say E equals all values of X such that X is an element of E, which means the even natural numbers. Okay, so let's go down and talk about the notation. So this symbol right here means is an element of. So for example, we read this 2 is an element of this set, or 2 is an element of A, which would be what we would call the whole set. When you have the symbol with the line through it, that stands for is not an element of. So for example, 4 is not an element of the set 2, 3, 5, 7, or 11 because it's just not included in that set. Okay, so the next example, designate the set S with elements 32, 33, 34, 35, etc. using the roster method. So they tell us in the directions that we're going to call this set S. So I start by saying S equals. For roster method, roster means that I need to use curly brackets. So I'm going to say 32, 33, 34, 35, dot, 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 and then I'm going to end it with curly bracket. Okay, this dot, 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 this is called an ellipsis, in case you see that in your homework. Anything that needs to continue on forever, you can use that ellipsis. And then the descriptive method, I'm just going to write it out in words. So I could say S is the set of natural numbers. I could also say whole numbers. I could also say integers because all of these numbers are all three of those things. Starting at 32. So again, there's not one right way to write the descriptive method. So I could have said S is the set of whole numbers starting at 32. S is the set of integers starting at 32. Or I could have said S is the set of natural numbers greater than, 31. There's lots of different ways to write it. Set builder notation. I'm going to start with S equals curly bracket and X in a vertical line. So I always start with this part. And then I describe what X is. So I'm going to say X is an element of N. Remember, that just means X is a natural number. And then I'm going to describe it even further, and I'm going to say, and X is greater than or equal to 32. I could also say just greater than 31, but I want to make sure 32 is included. So there's more than one way to write that. And that describes the set above. So 3 different ways that really accomplish the same thing. So let's talk about finite and infinite sets. So I've talked about this a little bit. I just mentioned the ellipsis and what that means. So anytime a set has a specific number of elements or no elements, then we call it finite. So if you don't see the dot, 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 that ellipsis, then we say that's a finite set, it ends. A set that is not finite, so that means it goes on forever, as noted by the ellipsis, dot, 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 then we call it an infinite set because it goes on forever and ever. Okay, so a couple of questions. So is the set PQRS finite or infinite? This would be a great place to pause the video and try these 3 on your own. I'm going to say it's infinite because there's 4 elements. You can count them. Is the set 10, 20, 30, dot, 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 finite or infinite? I'm going to say it's infinite because of the dot, dot, dot. Is this set, this would be what we call the empty set, which we're going to get to next. Is it finite or infinite? We're going to say finite because of the definition above. So the definition of a finite set means that it has a specific number of elements or no elements. So it includes the empty set there. So speaking of the empty set, let's define that. So an empty set is a set with no elements, and we call it the empty set. It can be written in 2 ways. So it's either 2 curly brackets with nothing in the middle, or we've got this, it looks kind of like the no smoking sign. When you're on connect, you'll have the option, remember curly brackets you have with your keyboard, and then this symbol right here with the circle and the line through it, this is on the math palette that pops up. So there's a palette with, it looks like a calculator where you have all the numbers, and then there's just, there's some different buttons there. It's got one of these empty set symbols on there, so you'll be able to select it if you need it for this section. So let's do an example. So which of the following sets are empty? The set of woolly mammoth fossils in museums. And actually this would be a great place to pause the video and try these on your own first. I'm going to say that this set is not empty because there are woolly mammoth fossils in museums. So to this day. So there are woolly mammoth fossils in museums. Okay, I'm going to make my pen a little bit skinnier here. Okay, the next one, all values of x such that x is a living woolly mammoth. I'm going to say this is empty. So we could just draw that symbol because there are no living woolly mammoths. Okay, and last but not least, this one's kind of weird, but you've got a set here and the empty set inside of it. So technically, we're going to say this is not empty because the set has the empty set inside of it. So this section in this module in general, you know, there are definitely some concepts that appear to be simple to understand, but they really, they're not as simple as they look, such as this one. So you've got double sets here because those outer curly brackets, that refers to the set that we're considering to be finite or infinite. And then even though there's what's in it is an empty set, it's still considered a set. So we say it's not empty. So with sets, if they're finite, it's helpful to sometimes count how many items are in a set. So for example, like if a scientist is studying animals, you know, they might want to know, well, how many mammals are there if they're looking at the set of mammals, or how many amphibians are there in the set of amphibians. So to do that, to count them, we actually consider this number, we call it the cardinal number of a set. So the cardinal number of a set, a finite set, is the number of elements in A, and it's denoted as, because we oftentimes have shorthand ways of writing things in math, n of whatever the set is called. So this is going to be the set name, and that can vary, but we always use the lowercase n. So the way that we could write this, let's look at the example. So it says find the cardinal number of each set. So since this set is called A, the way we write it is we say n of A, and how you say this, we say number of elements in A. So when you see n of A like this, you want to say in your head number of elements in A. That's what that's standing for. And the whole purpose of the shorthand notation is just so we don't have to write this all out. So n of A in this case would be 6 because there's 1, 2, 3, 4, 5, 6 elements in A. And then in B, I tried to come up with some examples that could potentially be tricky, so we can also look at these ones. This could potentially be tricky because you have the dot, dot, dot in the middle. So it's not at the end, it's in the middle. So it's still a finite set because it's got a beginning and an end. But the dot, dot, dot was just used so that we don't have the author or whoever wrote this doesn't have to list out all the numbers in between. So n of, I'm going to say n of B this time because this set name is B. And I'm going to count all of these numbers. Now the key though is that you have to count the middle. So at this point I would probably just write this all out. So it looks like 10, 12, 14. Looks like this is a set of even numbers going up to 30. So starting at 10. So I'm going to keep going. And then we've got 28 and then 30. So now we can count them all. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It looks like there's, did I count that right? Let me count it one more time just because I have 11 in my answer key. Oh, you know what? And I forgot. I'm glad I double checked. I forgot 20 there. There we go. So 18, 20, 22. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, cool. That matches up. So the number of elements in B should be 11 there. So another thing that we like to do with sets, so we can count the numbers, we can talk about the elements, we can talk about whether or not sets are equal or equivalent. So those two things mean different things, or those two words mean different things. So when two sets have the exact same element, so the exact same element, that's important, so I'm going to highlight that. Exact same elements, when they have the exact same elements, we consider them equal. So for example, let's say set A is the set of elements 1, 2, 3, and 4. And I'm just making this up. Let's say set B is the set of numbers 1, 2, 3, and 4. And they don't even have to be in order. We can say set A is equal to set B. When two sets have the same number of elements, they are considered equivalent. Okay, and equivalent, we use the symbol. It looks like there's a squiggly line and then an equal. So for equals, we just use an equal sign, and then equivalent sets, we use this sign right here. Oh, and you know what? I put that right down here. I must have missed that. So let's do an example for equivalent. So C, let's say set C is 1, 2, 3, and 4. And let's say set D is 3, 4, 5, and 6. They don't have the exact same elements, so they do have some in common, like 3 and 4, but they're not the exact same. But they both have 4 elements, so we can say that C is equivalent to D. And actually, if you look above, is A equivalent to B in the example above? Are there the same number of elements in A as there are B? And the answer is yes. You can actually say A is equivalent to B also. So they're equivalent and they're equal, as opposed to C and D, they are only equivalent. And another way to tell whether or not a set is equivalent, and I've actually got this in the bottom of the page here, is to do a one-to-one correspondence. And all that means, a one-to-one correspondence, you may have heard this, sometimes teachers will use this with younger children, so like kindergarten through like maybe first grade, when kids are first learning how to count items. So let's say a teacher puts 5 crayons on the desk, and they'll ask the young child, they'll say, can you count the crayons? And the child will take their finger, and hopefully if they do it correctly, they'll put their finger to each crayon and count 1, 2, 3, 4, 5. And if they can do that, the teacher says, okay, well, they passed one-to-one correspondence. That's actually an item on the grade report for kindergarten and first grade. If they cannot put their finger and match that up to each item and count, then they say that, well, they need to work on their one-to-one correspondence. So in this case, the one-to-one correspondence just means that, I'm going to use a different color, that you can match up. So like the 1 goes with the 3, the 2 goes with the 4, the 3 goes with the 5, the 4 goes with the 6, and the matching isn't significant other than the fact that as long as they each match up with each other, then we say, yes, they have one-to-one correspondence, so therefore they are equivalent, because if they are equivalent, they have the same number of elements, so one-to-one correspondence would have to occur. So let's look at this example. So this would be a great place. Pause the video and try this on your own. So state whether each pair of sets is equal, equivalent, both, or neither. So A, they both have 4 elements. So I'm going to say they are equivalent. They are not the same elements though, so they're not equal. Set B, I've got 2, 13, and then 2, 1, 3. So I put this on here, on purpose, just so we can look at one that might be potentially tricky. So this set has element 2, 13. It has 1 element. This set has 3 elements. So I'm just going to write that down. So this has 3 elements, 2, 1, 3, and this just has 1 element. So they are not equivalent and they're not equal. They are different sets. So same digits here, but not the same or equivalent. So I'm going to put N, or I'll just write neither. And then for this one, all values of x such that x is a part of E. So remember, E is even natural numbers. So I'm just going to write a little note. So even natural numbers, so that would be like 2, 4, 6, 8, those numbers, and x is less than 10. So actually, let's write that out even. Well, I was actually off to a good start, because less than 10 would be 2, 4, 6, 8. So less than 10 means not including 10. So that's what this set builder notation describes, even numbers between 2 and 8. And then 2, 4, 6, 8. Well, it looks like those sets are equal and they would be equivalent since they have the same number of elements. So I mentioned this, but let's just fill in the blank to be thorough. So two sets have one-to-one correspondence of elements if and only if each element in the first set can be paired with exactly 1 element of the second set and vice versa. So let's show that these two sets have a one-to-one correspondence. So if you wanted to, you could leave them there and just use arrows, or you could actually write them right on top of each other like this, and then you can just match them up. So you could say, well, these match up, these match up, these match up, and these match up. So therefore, there's one-to-one correspondence. And then let's think about it. If two sets cannot be put into one-to-one correspondence, would they be equal or equivalent? Explain. So two sets cannot be put into one-to-one correspondence. So what would that look like? So if they cannot be put into one-to-one correspondence, it means that they must have a different number of elements. So one's bigger than the other. So is it possible for them to be equal or equivalent? And the answer would be no. So they're neither equal or equivalent. It wouldn't be possible if they cannot be put into one-to-one correspondence. Okay, so let's talk about section 2.2. So 2.2, set subsets and set operations. The universal set is symbolized by the letter U, a capital U, and is the set of all potential elements under consideration for a specific situation. So I know that this might seem overwhelming, and it's hard to understand what this means now, but just let's write this down, and then I'll do an example below, and hopefully this will make more sense. The complement of A is denoted by A and then an apostrophe. So the apostrophe, that's what tells you that we're looking at the complement. And it means all the elements in the universal set that are not in set A. So let's do an example. So let U be the set of elements V, W, X, Y, Z, and then we've got A here. Find a complement and draw a Venn diagram that illustrates these sets. Okay, so this is the first time that we talked about a Venn diagram. So what is a Venn diagram? So you may have seen these and used them before, hopefully so, but if not, that's okay. So we always start with a rectangle, and then however many, we'll draw circles for all the different sets. Now in this case, we're only going to draw a circle for A. The universal set, the U, that's basically all the elements that are in the rectangle. It doesn't necessarily mean that there's going to be a circle with all of those elements in it. So when you see the U, you don't want to draw a circle for the U. You only want to draw a circle for the other sets that are listed in the problem. So if there's only, in this case, we only have A. So if A has W, Y, and Z in it, we want to put those inside the circle. If the universal set has V, W, X, Y, Z, anything that this has that's not in A, we want to put on the outside of the box. So V is not inside of A, so I can put it anywhere I want outside the box. W is in A, so that's covered. X is not, so I'm going to put X on the outside of the box. Y is in A, and Z is in A. So here's our Venn diagram, and then it says find a complement. So if A is the set W, Y, Z, then a complement would be the set of elements that are not in A. So in terms of the picture, what that would look like, it would mean the outside, everything that's not in A, which would be, it'd be the X and it would be the V. So not in A would be X and V. So it was important that we knew what that universal set was, because otherwise, if we only had A, we wouldn't know what went on the outside of the box there. So we'll be drawing a lot more of these pictures to come. So if that didn't make complete sense, don't worry. We've got lots of examples coming up that'll hopefully help clarify this a little bit more. So the next thing we're going to talk about is subsets, and we can't really talk about sets without talking about subsets. It's a really important part of talking about sets, because when we're thinking about groups of things, so go back to my initial example about animals, for example. If you think about all the different types of animals out there, some of those types of animals fall inside of other groups. So for example, we could say like all bears, for example, all bears are mammals. So the set of mammals is a set of all types of animals, and the set of bears is a part of that group. Now there are other animals that are also a part of the mammal group, but bears are, the entire group of bears is a part of that. And the way that we talk about that with math language is we say the set of bears is a subset of the set of mammals, because all of those bears are part of that larger group of mammals. So the mathy way to say this would be, if all the elements in set A are also in set B, then A is called a subset of B. And the way they are denoted with, it looks like a sideways U with a line underneath. So subsets are denoted by this symbol and are the set of elements that are contained in another set. So here are some facts to consider. So every subset, or every set, is a subset of itself. So for instance, we could say that if A is the set A, B, C, D, technically we can say A is a subset of itself. Why? Because of the definition. All elements in A are a part of A, because it's the same thing. The empty set is the set of every set. So we could say that the empty set, we could use this symbol, is a subset of A. One way, this is one that always kind of tripped me up a little bit when I first started learning about this, because I thought, well, that's weird. The empty set doesn't have anything in it. Well, if we think about it this way, if we think about, is there anything that's in the empty set that would not be in A? And the answer is no. Like, it doesn't contain anything that would be outside of A, so by definition we would have to include it. And then lastly, if a set is not a subset of another set, we denote it with this symbol. So we use the same subset symbol, but then we just put a line through it. So for example, if we take this example up here, A is A, B, C, D, and let's say I have the set B, which has elements B, F. Now notice B, lowercase b, is a part of A, but F is not. So I would say that B is not a subset of A, because all of B is not inside of A. So let's do another example. So find all subsets of A, American Idol, and Survivor. So when we have to list out all the subsets, what we're doing is we're listing out every set that would be completely included in A. So one example would be the set with just American Idol, because American Idol is a part of this bigger set. One would be the set of just Survivor. One would be the set itself, American Idol and Survivor. And the other one would be the empty set, or you could use this symbol. So it's either or there. So if the set that in the beginning has 2 items, there's actually 4 subsets that can be listed there. Let me do one more example that looks a little bit more similar to what you're going to see in your homework. So I'm going to actually erase this real quick. So similar, but let's say, so this is going to be like example 2. Let's say you had a set with items 2, 3. So the subsets, if we listed them out, would be 2, the set with 2, be the set with 3, it'd be the set with 2, 3, and it'd be the empty set. So all the different possibilities of different sets you could make with that beginning set, that would be a part of it. And again, I know it's weird to put the empty set in there, but remember that was part of the subset facts, that the empty set is a subset of every set. So now that we've got that down, let's talk about what a proper subset is. So it's really similar to what we just discussed, subsets, but it's with one main difference. So if A is a subset of B and is not equal to B, so there's one exception there, then we call A a proper subset of B, and we write it with its very similar notation with that sideways U, but there's no bar underneath it. If a set is not a proper subset, then we use that symbol and we put a line through it. So let me do an example. I know this next one says find all the proper subsets, but I'm actually going to do both. I'm going to do proper subsets over here, and then I'm going to do subsets on the right so that you can see what they would look like next to each other, so you can see the difference. So all proper subsets of x, y, z, you list out all the subsets. So x is a part of x, y, z. Y is a part of x, y, z. Z is a part of x, y, z. X, y is a part of x, y, z. X, z is a part of x, y, z. Y, z is a part of x, y, z. And then let's see, we've got 1, 2, 3, 4, 5, 6, and then we cannot list the set itself because in order to be a subset, it cannot be equal to the beginning set. So we leave out the set of all the original set that we were given in the problem. So we do include the empty set though. So notice for 3-element set, there's 1, 2, 3, 4, 5, 6, 7 elements. So there's 7 elements here. Well, not elements actually. You know what? I'm going to say 7 proper subsets. It's a better way to say it. And then with subsets, okay, it's very similar. You're just going to include the whole set. So for subsets, you would list the same ones. So x, y, z, x, y, x, z, y, z, and then you would also list x, y, z there and the empty set. So let me actually use a different color. So x, y, z, so that's the only difference between these two problems, is that a subset includes the set itself. So subset, there are 8 subsets. So there's one more subset than proper subset. Okay, so let's do a couple of examples below. And this would be a great place to pause the video and try it yourself. So state whether each statement is true or false. So the set 1, 3, 5 is a subset of 1, 3, 5, 7. The definition of subset means all of these items are inside of this set, and that's true. Okay, B, the set AB is a proper subset of AB. Now, A and B are both in A and B, so this would be a subset of itself, but the definition of proper subset says that a set cannot be a proper subset of itself, so I'm going to say false here. But the set AB would be a subset of itself. It doesn't ask for this, but I'm just clarifying in case you're wondering. And then lastly, the set 2, 10 is not a subset of 2, 4, 6, 8, 10. Well, 2 is inside of the set, 10 is inside of the set, so I'm going to say false. 2, 10 is a subset of 2, 4, 6, 8, and 10. Okay. So if you're wondering, like above, I know you may have noticed that with the 7 proper subsets versus the 8 subsets that they differ by 1. There's actually a formula for finding the number of subsets, and it can be handy if you don't want to list them all out because it can get pretty time consuming, especially if you have a set with a lot of elements. So there's actually a formula for finding the number of subsets. So if you notice up here, there are 3 elements in this set, and there are 8 subsets and 7 proper subsets. If you take 2 to the 3rd power, 3 because there's 3 elements, then you end up getting 8, which is the number of subsets. So the formula for finding the number of subsets, and I'm going to highlight this, the formula for finding the number of subsets is 2 to the nth power. And the formula for finding the number of proper subsets, so I'll highlight that too. So proper subsets is going to be 2 to the nth power, so similar to what I just set up there, minus 1. So we're going to subtract the 1 there. So for example, find the number of subsets and proper subsets of this set, 1, 3, 5, 7, 9, and 11. Now it would take a long time to list those all out, so we're not going to do that, but I'll just use the formula. So there's 1, 2, 3, 4, 5, 6 elements. So we can say n equals 6. So in the formula, n equals the number of elements in that original set. So subsets, So the number of subsets that this set is going to have is going to be 2 to the 6th power. And if we do that, we get 64. And then the number of proper subsets is going to be 2 to the 6th, which is 64 minus 1. So 64 minus 1, or 63. So I mentioned in the beginning that we'd be doing very little calculations, which is true, but we are going to do some calculations. They're different than the calculations that you've been doing so far in this class, where there's a lot of numbers and you're actually calculating adding, subtracting, multiplying, dividing, that kind of thing. But there are actually some interactions that happen between different sets. And so we're going to talk about those. So the first interaction we're going to talk about is called the intersection. So the intersections of two sets, A and B, is denoted by this symbol. It looks like an upside down U. So this upside down U is called the intersection. I also like to think, every time I see this symbol, I tell students to think of the words in common. So when you see that symbol, think, what do these sets have in common? And in terms of the Venn diagram, the part that they have in common is going to be the middle, or this part of the set. So if we call this set A and the set B, the part that they overlap, that's going to be the part that they have in common. So this picture shows A intersect B, or what does A have in common with B? We can also say it in words. We can say this is the part A and B together, so what they both have in common. And so we say A intersect B, and remember, this just means in common. Let's do an example. So we're given some sets here, A, B, and C, and we're asked to find A intersect B. Now you could totally, if you want to draw a picture, you can. So you can draw a Venn diagram, and you can have A, 3 circles, A, B, and C, and you can, oh, that doesn't make sense. I labeled that one circle A and B. So A, how about this? There we go. And you can put the numbers where they need to go, and you can visually try to find what they have in common. That's one option. I actually think this is easier to not draw the picture, and I know that might sound weird. Normally I'm encouraging students to draw pictures, but I think this is simple enough just to look at visually, compare the two sets. So let's look at A and B. So if I'm going to actually write this out again, I know it seems like a lot of work, but it's worth it, I think. So when you're finding the intersection of two sets, I really like to write them out so that they're right on top of each other. And that way I can look and see what they have in common. So it looks like they both have a 10, and it looks like they both have a 20. So the answer for this is going to be 10, 20. And when you're doing your Connect homework and you're asked to do this, find the intersection, remember you've got to put your brackets when you type this into the computer. And you can always click on Show Example to look at how the example is written, the answer for the example, and that's exactly how you're going to want to write your answer when you do it. And then let's do this next one. So A intersects C, we're going to do the same thing, except we're going to list out A and C. So I'm going to list out A is 5, 10, 15, 20, and 25, and then I'm going to list out C is 30, 50, 70, 90, and I'm going to look and see what they have in common. Now in this one, I don't see anything they have in common. So this is a great place. This is why we have notation for empty set, because if I'm comparing two groups of things and there's nothing in common, then I need a way to write that. So I'm just going to write down nothing in common. So the answer is this. And on Connect, if you had to do this, you could either put the empty set symbol, which is going to show up on that math palette that you can click on, or you can enter in the curly brackets with nothing in between, and you can use your keyboard for that. So either one. So this next term, disjoint sets. This is important sometimes because there's many times in life where we'll have groups of things where there's no overlap, there's nothing in common. And when there's nothing in common, or mathematically speaking, the intersection of two sets is the empty set like we just had, the sets are said to be disjoint. And disjoint sets, you can even draw on a picture. You can show a Venn diagram where there's nothing in between, or you can draw disjoint sets as completely separate circles if you want, because there's nothing in common. Okay, and so next we're going to talk about union. So the union of two sets is we draw a symbol. It looks like a U. It's different than the letter U on your keyboard, but it looks like a U. And actually, if you need to type it on the computer, you actually need, like in Connect, you need to use the math palette. There'll be this symbol there for you. And this stands for the union. And the word that I like to think of when I see this sign is I think of the word combine. So every time I see intersection, upside down U, I think in common, and anytime I see this symbol, I think combine together. So union, you could also think of marriage, like when two people become married, they're combining their lives together, so they're pooling everything together. You could visualize that when you see this symbol to help you remember it. So let's draw a picture. Let's call this circle A and this circle B. If we were to combine A and B, it would mean that we'd take anything that was in A, anything that was in B, and anything they have in common. So anything that's in that shaded region, that would represent A union B. And again, think combine together. And in words, we could say A or B. Let's do an example. So we've got some sets below and we're asked to find A union B and A union C. So I'm going to write down A union B first. So what this means is it means to combine sets A and B together. So whatever they have, we're going to list it. So if A has a 0, we put it down. If A has a 1, we put it down. A and B have a 2, we include the 2. A has a 3, B doesn't, but I include it. 4, I'm going to write down. 5, and then we've also got 6, 8, and 10. Notice the ones that were in common. So like, for example, they both have a 2. I didn't list that twice. I only have to list it once if they have it both in common. But if there's an element that's only in one of them, so like the 5, you still list it. So you put everything together. And then let's do A union C because we're asked to find that. So we're going to combine A and C together. So I'm going to start with 0, 1, 2, 3, 4, 5. So I'm basically putting everything in A and then I'm going to put everything in C. I already wrote down 1, already wrote down 3, already wrote down 5, but I'm going to write down 7 since I don't have that. And so everything in this set here is all of the numbers that are in A or C. So where this gets tricky is when we start to do multiple set operations at the same time. So, well, and I shouldn't say same time. You do them one at a time, but they're all within the same problem. So let's check out this example below. So we're asked to find, it says example, we've got a set A, a set B, and a set C, and we're asked to find A union B intersects C. So the first place that you want to start, you want to treat this kind of like the order of operations. You don't want to try to do this all in one step. You want to always start in the inside of the parentheses. So you're going to do this first, and then you're going to find what that has in common with C second. Okay, so the first thing I'm going to do is I'm going to write A union B, and I'm going to write out that whole step. So that's step 1. Inside of the parentheses first. So A union B means to put all of these letters together, and if there are common letters like O, you only list them once. So I'm going to write down L, M, N, O, P, and then Q and R. Now I write them in order, but you don't have to. The order really doesn't matter. I like to order because it helps me do the problem. It makes more sense in my brain, but it's not necessary. And on Connect, you should be able to write your answers in any order and still get marked correct. And then lastly, we're intersecting that with C. So what we're going to do, I'm going to write C right below it. So C is R, S, T, and U. and I'm going to see, remember that this upside down means in common. So I'm going to look and see what they have in common. And it looks like the only thing they have in common is the R. So the answer to this problem is going to be R, and that's it. So we did A union B, we combined them, and then we intersected that with C, found out what they have in common, and R was the only element. And again, if you were to do these problems, one of these problems, and you find that they don't have anything in common, that's okay. You just put the empty set. Okay, so let's go down to the next couple of examples. So in this example, notice that we're given U here. That's all of the numbers that are to be considered for this problem. And we need that because this problem has a complement. So remember this symbol here, that apostrophe, means what's not in A. So I'm actually going to write that. This is complement. And we say what's not in A, what does that have in common with what's not in C? So I'm basically just writing this out in words, what I need to do. So if A is 10, 30, 50, 70, look at what's in U. And I want you to tell me what is not in A. So what is A missing? If A is 10, 30, 50, 70, then it's missing a 20, it's missing a 40, it's missing a 60, and it's missing an 80. So I'm going to write down 20, 40, 60, 80. That's what's not in A. And then what does that have in common with what's not in C? So let's look at it. C. If C is 20, 40, 60, what is not in C? Well, C is missing a 10, a 30, a 50, a 70, and an 80. And so remember that this symbol means in common. So what do those have in common? Well, it looks like the only number that these sets have in common would be the 80. So the answer is just going to be the 80. So that's your answer. And then this next one down below, we've got some parentheses again. So we're going to do this. I'm just going to put a little number 1 here. That's going to be first. The apostrophe is going to be second. And then the in common part, that's going to be third. So we're starting on the inside of the parentheses and we're working out, okay? So it's important that we go in that order. Okay, so let's start on the inside of the parentheses here. So A intersect B. So I'm actually going to I'll write these up here. So A is 10, 30, 50, 70. B is 40, 50, 60, 70. What do they have in common? So A intersect B. Let's look and see what they have in common. It looks like they have a 50 in common and they have a 70 in common. So I'm going to write down 50, 70. That's A intersect B. That's what they have in common. And then next, so the second step is to find the complement of that. So A intersect B complement means what's not in this set 50 and 70. So I'm going to look at the universal set and I'm going to list out all of the numbers except 50 and 70. So 10 is not included in this set, and then 20, 30, 40, 50 is, so I'm going to skip 50, 60, 70 is, and then I'm going to write down 80. So what's not in this intersection is 10, 20, 30, 40, 60, and 80. So I'm finished with steps 1 and 2, and then I'm going to intersect that with C, and I'm going to write down all the elements in C. So C is 20, 40, and 60. So what do these two sets have in common? And it looks like they both have a 20, and they both have a 40, and they both have a 60. So the answer is going to be 20, 40, and 60. So you can see that was not fast. I would never attempt to do this problem in my head. I know students who prefer to draw a picture, and if you want to try that, you can totally do it. I find that more students have success with just writing it out this way. But like most math, there's lots of different ways to approach this, so don't feel like my way is the only way. So we're getting to the end here. We need to talk about subtraction. So set subtraction is just referring to the difference. So we can use difference to the word difference to describe subtraction. It's the difference of set A and set B, and there's a explanation there. Let's actually just do the example as we talk about this explanation. So when you subtract A and B, what I would advise is to write the sets out. So write out A and then write out B below, just like if you were subtracting in a math class. So if I say, for example, subtract 68 minus 24, a lot of times, especially when you're learning this in elementary school, you write 68 minus 24 vertically and you line them up. Well, we're going to do the same thing here. So the definition of subtraction, A minus B, you're going to ask yourself, what is in A but not in B? So one way to do this is to just cross off anything they have in common. So if they both have a 6, so I cross those off and that's it. And then after you cross off what they have in common, ask yourself, well, what is left over in A that's not in B? And the reason we cross off the 6 is in B, so I don't want to include that. But what's left is a 4, an 8, and a 10. And so A minus B is equal to 4, 8, 10. So if you like to write out the process when you're subtracting, you're going to put them vertically on top of each other. You're going to cross out what they have in common, and whatever is left in that top set or the first one in the problem, the subtraction problem, that's going to be what's in your answer. Okay, so hang in there. We're almost done. We've got to talk about Cartesian product. So it sounds fancy, but I promised it won't. It's not too bad. So the Cartesian product is denoted by A times B. So when you see times, that means an A and B are sets. Times means take the Cartesian product. All you have to do is match everything up in the first set with all of the elements of the second set in coordinate pairs. The order does matter though. So, and I'll show you, we're going to do A times B and then B times A. So A times B, you take the elements in A, so 1, and you'd match it with B, the elements in B. So for example, we'd have 1, 2, 1, 4. And then we do 3, 2, let me erase this. Then we do 3, 2, 3, 4. I could put commas between these. And then we do 5, 2, 5, 4. So the Cartesian product, A times B, is the set of these ordered pairs. So you always write the Cartesian product with curly brackets. And again, those are on your keyboard or in the math palette. When you do B times A, it's going to be the other way around. So you're going to start with an element of B. Let's start with 2, and it doesn't matter. You could start with 2 or 4. You'll get it right either way. You start with 2 and you match it up with all of the numbers in the other set. So we've got coordinate pairs 2, 5, 2, 3, and 2, 1. And then we're going to do 4, 5, 4, 3, 4, 1. Okay, so it looks like we've got 1, 2, 3, 4, 5, 6 elements in A times B and 1, 2, 3, 4, 5, 6 elements in B times A, but they're not the same. So just keep in mind when you're doing the Cartesian product that the order does matter. So I hope that helps. Keep in mind you're going to need lots of practice with this. Feel free to email with questions when you have them. And then as you're doing your homework, if you're having trouble with the set operations, feel free to take a picture or a video and send that to me so that I can see what you're working on and help you troubleshoot.